guys. This is, if you pay attention to the name of this PowerPoint, it's the PowerPoint in Moodle, which has solved examples. You can go through this PowerPoint. It has some solved examples, and they're very nice examples. But I just want to go with you through this PowerPoint to explain to you the things that we are not going to focus on, or we are not going to cover it in this semester. So I want you to be clear about the things that we will focus on and the things that we will not cover it in this semester. So you will not be overwhelmed with bigger material unnecessarily. This is example. First of all, this is section 6.1. This is example. Let's read together. It's a 1,200 Newton plate rests on floor. Rests. It means no movement. How much work is required to move it at a constant speed? Acceleration is 0, of course. How much work? Work is equal F times D. So keep in mind, we are looking for F, we are looking for D. It says 5 meters along the floor against the friction of 230 Newton. Just stop here. So how much work is required to move the object 5 meters along the floor against the friction of 230 Newton? He did not tell us the applied force, right? He just gave me straightforward the displacement that we're going to move, this box or plate, but he mentioned something. He said we want it to be against this friction force. So if the friction force is 230, if we apply a force just above the 230, then we can, of course, move that object to 5 meters. So we can assume that the applied force is the 230. Alright? So if the applied force is 230, so this is the object, the applied force will be exactly the amount of the kinetic friction. Alright? So it is the 230. And of course, displacement, it says that it will move 5 meters along the force against the action force. It means we are also moving on the same line. Alright, so the applied force is 230. The distance is 5. What is the angle between the applied force and the distance? It's 0. So it is F applied times D times cosine 0, which is 1. Alright? So it is simple. Like, the only point here that you have to get it, that the applied force is the force which is equal in the amount of the friction force, okay, to overcome the friction force, basically. Okay, now part B, it says how much work is required to move it 5 meters vertically. This is horizontally. What about vertically? Again, this is the object. So this is surface. This is the object. And he wants us to move the 5 meters vertically. 5 meters. Alright. What we have forces vertically? We have the Fg, which is the 1,200 Newton, right? And we can apply with a normal, basically here there is a normal force, alright? But how to move the object? If you recall the problem of the box that we took in chapter 4 over and over and over, it was if we apply with a force equal into amount to the normal force, then we can move the object up. So exactly what we are looking for is that amount which can overcome the force of the gravity and the normal force, basically, which is 1,200 Newton. So you can say the applied force is 1,200, alright? The distance is 5, also the angle is 0, alright? Which is 1. So this is the work required to move the object vertically. Alright? Okay. Here it is the same concept, but with an inclined plane. This is a box. It is on an inclined plane, very small inclination, which is 9 degrees. And it says, what is the minimum work And actually this one also is a minimum work. He should say what is the minimum work, because the minimum work is required to overcome friction force. Here, the minimum work is required also to overcome the gravitational force. Okay. So here, it says what is the minimum work? This is really a good, accurate question. Needed to push 950 kilogram car 710 meters up. Right? So where is the direction of the movement of the car? This is the direction. Right? We want to move it 710. Okay. So we want the minimum work which is required for that. We also don't have a straightforward applied force value. We try to see that which force are we trying to overcome, and that will be the minimum amount of force that we want to apply. Okay. If we just for a minute assume that this is the object and this is the inclined plane, if we leave it, it will fall down to this direction. And the effect of which force? Is it the normal force, gravitational force, or only the x component of the gravitational force? Let me again go back to the simple inclined plane. This is the object. If you just leave it as it is where it goes, it will go down. And we mentioned earlier that it will go down under the effect of the x component of the gravitational force. So basically this is the force, the x component of the gravitational force that we are trying to overcome. Alright? We calculate this force, and this will be our required force to apply to be able to move. So we calculated mg sine theta, sine 90, and it's equal to whatever the amount. Then we say the work is equal to that force times the distance, and don't forget that force will be up and the distance up, so that the angle is 0. So the work is this minimum force, which is the value exactly like this one, times 710 times cosine of 0. Alright? And this is additional, that if he's asking you what is the work that is resultant work due to the normal force, this is the displacement, this is the normal force, the angle is 0, they're perpendicular to each other. So there is no work done due to the normal force. What about the y component of the gravitational force? Also there is no work done due to the y component, because it's also perpendicular to the z. The only work is due to the x component, basically, of this gravitational force. Okay, guys? Just you always read the problem and see which thing he's asking you. Don't go through all this analysis. If he's asking you the minimum, it means which force you will overcome. This force. Calculate it. This is the distance, and the angle between them is 0. That's it. Work energy principle that I explained earlier, that work is equal to the change in the kinetic energy. Okay. Basically, this is a simple problem. How much work must be done to stop? To stop, it means V final. The word to stop, it means V final will equal to 0. And this is the mass. And the car is already moving, which is the initial. So what we have here, he's asking for work. He's not giving me force, he's not giving me distance, angle, nothing. He's giving me simply M, V initial, and V final, which is very clear indication of kinetic energy, half mv squared. And this is V initial, V final, so it is change in the kinetic energy. Alright, so we think immediately about work energy principle, where work net is equal to the change in kinetic energy, which is half M V final square minus V initial square, right? And let's do it. And V final is equal to 0. So the work is negative. Why the work do you think is, and be careful, it's in the limits of 2 we want to stop a car. Right? So we are going against, so that if the car simply is moving in this direction, the force which should be applied should be against. So the angle between them would be 180. That is normal. When you want to stop the car, you want force against the direction of motion. Right, guys? So it makes sense, the negative sign. Alright. Let me go through. We can go through this example. Okay, here. Guys, you know that not all the forces will be having a work done due to them. For example, if you are applying force on this object upward, right, and the motion is, of course, is upward, what is the angle between F external, which is applied by your hand, and D? The angle is 0. So what is cosine 0? It is 1. So will there be any work? Yes, because cosine 0 is 1. So F external times D cosine theta will have a value. Alright? And if you recall, in the previous YouTube, we mentioned that to move the object from place y1 to y2, we are literally, if we consider this is to be our 0, so we are moving it from a potential energy 0 to potential energy mgh. So the change in the potential energy, which is delta BE, is equal to work done to move the object from here to there. Alright, so F external D cosine theta is equal to change in the potential energy. Alright? We will not be talking about any example related to the string. Alright, guys? So this the string. We will not solve any problem related to the string. So anything related to the string for this semester we will not solve it. This is important because many problems you will see related with the string. Now here there is another example. It's a very simple example, but you have to pay attention to the reference point. It says a 160 meter tall person lifts a 1.65 kilogram book off the ground, so it is 2.2 meter above the ground. That literally, the book was here, okay, and it was left, and it reached to, like what did he say, above the ground, maybe bookshelf or something. He left it till here. Okay, so the total elevation from the ground was 2.2 meter. He said, what is the potential energy of the book relative to the ground? It is mg times 2.2. That when he said relative to the ground. What if he says, so this is our 0, so relative to the ground, it is mg 2.2, right? Now, if he said, what is the potential energy with reference to or relative to the top of the person's head? The person himself was 1.6 meter. So if we are calculating the potential energy with reference only to his head, what is the potential energy? mg times this difference, which is 2.2, minus 1.6, which is 0.6 meter. So mgh with reference to the person head is simply, let's see here the number. The potential energy with respect to the ground is 35 point something joule. With respect to the person head is only 9.7 joule. You can see completely different two answers. So you have to always pay attention what is the reference point that the question is asking. Okay, and this is about spring, we don't want it. About spring, we don't want it. Now here we want them, alright? And these are about the roller coaster, which I saw a lot of them in the previous example, okay? Or in the previous YouTube. These are very important examples also. This one, if I have to